joining me. I know everybody has a busy schedule that's made even busier these days. So I definitely appreciate that. So yeah, as Megan mentioned, this is part one of a three-part series of discussions and presentations. And in this first one, what I'm going to do is talk mainly about the science behind global warming and climate change, and why it's happening, what's causing it, and I'll get to some of the very basic impacts. But the second talk next week will be specifically impacts focused on Illinois and the Midwest, but also global impacts. And then the third, talking about climate justice, which is an important piece of climate change information. There we go. So as Megan mentioned, my name is Trent Ford. I am the Illinois State climatologist based at the Illinois State Water Survey, part of the University of Illinois at Urbana-Champaign. I am originally from Illinois, from Roanoke, Illinois, a little town in Woodford County, about 1,800 people. I'm actually a geographer by training. So I got my bachelor's degree in geography from Illinois State University. So I'm a Redbird. And then master's and PhD in geography from Texas A&M University. After with a geography with a specialty in climatology and climate science. After graduating from Texas A&M, I worked for 4 years as an assistant professor in geography and environmental resources at SIU Carbondale. So I've kind of been all around the state, and know the geography and the climate of the state pretty well. More professionally, I'm a hydroclimatologist, which means that my research deals a lot with how the hydrologic cycle interacts with the climate system, especially as it relates to extreme events like drought and extreme heat or heat waves. Also, I do all sorts of things. I'm a dad. I actually barricaded myself in my bedroom right now because my 2-year-old will come home at about 4:30, and so if you do hear noise, then that's him. So let's get started with a little, and some of this information I'm going to present may be a complete background or refresher. It may not be new to anybody, at least in the beginning. But I really wanted to make sure we're all on the same footing when we start talking about how climate change affects, or global warming, I should mention, affects the Earth's energy balance. So I'll mention the climate system quite a bit. And we don't have to dissect this schematic here, but the climate system is not just the atmosphere, but also includes the land surface, the hydrosphere, all of the water, the cryosphere, all of the ice, sea ice, glaciers, and ice sheets around the world, and then all the way down into what's considered the critical zone, down into the unsaturated zone and saturated zone of the soil. So the entire system works and feeds back and interacts one system with another to create what we consider our climate system. And that, therefore, global warming, which is the ultimate driver of our changes in climate, it's not just a change in temperature or precipitation, but it has impacts down this chain that are quite diverse and comprehensive. And like I mentioned, the second talk will really talk specifically about the impacts. So to really understand the science behind climate change as we know it, we really have to think about the Earth's energy budget. And so I have the schematic here on the right-hand side. So of course, the sun provides all of the initial energy that drives our weather. And that shortwave radiation that comes from the sun enters our atmosphere, and it works to do several different things on Earth. It can be reflected and scattered in the atmosphere, can be reflected right back into space, and it can be absorbed either by the atmosphere or the Earth's surface. The energy that's absorbed, much of it is then re-radiated as a different type of energy that I'm calling here on the left-hand side terrestrial energy, or what we as humans feel as heat. So light enters the Earth system, heat leaves the Earth system. And over millennia, in general, the energy should be balanced. So I can consider this Earth's energy balance instead. Of course, if we are taking in more energy on Earth as an Earth entire, thinking about the entire Earth system, if we're taking in more energy than we're giving off, temperature will increase. If we give off more energy than we take in, temperature will decrease. And so that's kind of the simplistic way of thinking about how Earth's energy budget affects temperature on Earth. Now, this little guy right here, the greenhouse effect, is a naturally occurring process in the Earth's system. What it is that certain gases in the atmosphere allow the shortwave radiation from the sun to get into the atmosphere, get into the Earth's system. But when that energy is then re-radiated as heat, or the terrestrial radiation, those same gases absorb, or some folks will say trap, that energy here on Earth. So therefore, the concentration of these, what are considered greenhouse gases, the gases that cause this effect, they drive, generally on large scale, temperature variability on Earth on longer time scales. Now, there's several greenhouse gases, but as far as long-term Earth kind of time scale climate change, as well as the shorter human scale climate change that we're going to talk about over the next few weeks, these gases really can be distilled down to carbon dioxide, CO2, methane, which is CH4, and the gas form of water, H2O. And because those three gases in particular vary in time, the concentrations of those do, the climate, the overall temperature of the Earth, and therefore the climate of Earth also vary in time. Now, you may hear the term radiative forcing. I'll certainly talk about radiative forcing when we talk about climate projections, projections of changes in future climates. But radiative forcing is the forcing, the driving of Earth's temperature by energy, the changes in the energy budget through greenhouse gases. So if we go back to the beginning of Earth, some 4 billion years ago, carbon dioxide varies naturally. And over that long time period, carbon dioxide, the concentration of carbon dioxide in the atmosphere, is the primary driver of Earth's temperature variability, again, on long time scales. Now, if we think about human time scales, what I'm showing you here on the right-hand side, this is showing the observations of carbon dioxide concentrations at the Mauna Loa Observatory in Hawaii, all the way back to the late 1950s. And what you can see is that there's a consistent increasing trend in carbon dioxide concentrations. And indeed, we've observed this consistent trend in carbon dioxide concentrations over the last 60 years. That's really when we've been taking the direct observations on Mauna Loa. And to give you an idea as a point of reference, this says September 2019, because I forgot to update this, but September 2020, actually, we had 411 parts per million. That was the concentration of carbon dioxide in the atmosphere. So that's somewhat of an important number to hang on to when we talk about longer term historical. However, if we were to think back about 60 years, we would see levels in the atmosphere of about 310 to 320 parts per million. So we've increased about 25% to 30% over that time period. But there is natural variability in carbon dioxide concentrations, and that's what this graph is showing here. What this is showing on the top, I really want to pay attention to the red line here. The black line is reconstruction, so it's less relevant here, but the red line is showing observations of carbon dioxide concentration from the Dome C ice core in Antarctica going back 800,000 years. Ice cores are one means of trying to understand past climates, or what is considered paleoclimate. The great thing and the unique thing about ice cores with respect to other proxies like tree rings or coral is that in ice cores, because when the ice forms, the air in the atmosphere at the time the ice formed can be trapped in bubbles in the ice. And then the ice packs on top of each other over the several 100,000 years in Earth's long-term ice sheets in Greenland and Antarctica. And when the scientists drill down to take that ice core, they can extract and directly measure Earth's atmospheric concentration, its chemistry, that goes all the way back to 800,000 years. So instead of statistically reconstructing something, based off of a measurement that can represent something else, which brings around an error to it, these are direct observations. And so what we can see overall is that, going back 800,000 years before the present and now to the present period, we see carbon dioxide concentrations vary, and they vary pretty strongly. And the black line is a temperature reconstruction from the same measurements. And we can see that temperature co-varies with carbon dioxide. As carbon dioxide goes up, the greenhouse effect increases, temperatures on Earth go up, and vice versa as it goes down. One thing that we can see here, though, is that over the last 800,000 years, carbon dioxide concentrations have never exceeded about 300 parts per million. And if you remember, we're currently at 411 parts per million. Also, the increase that we've seen over the last 60 years with carbon dioxide concentrations is unparalleled for what we see here. Now, we certainly see large increases in carbon dioxide concentrations on this chart here in the red line, but when you think about the time scale on the x-axis, we're talking about large changes over tens of thousands of years instead of now what we're seeing over 60 years. So obviously there's a difference with our warming currently and our increase in carbon dioxide concentrations currently versus the last 800,000 years of Earth's history. And so, one thing that is really important here is attribution of that carbon dioxide, because carbon dioxide does vary naturally, and it's very naturally even in our lifetimes. What this figure is showing here, it's a figure from the IPCC, the Intergovernmental Panel on Climate Change, and from their report back in 2013. And what it's showing is the attribution of carbon dioxide concentrations and total radiative forcing, total global warming by source. And what the IPCC does is it breaks it down by what are considered anthropogenic, that's human sources of warming or cooling, and natural sources. As you can see, the only natural source of changes in temperature over the last 150 to 250 years are small changes in solar radiance, in how much energy the sun puts out, which only accounts for less than 1% of the total amount of radiative forcing that's taken place over the last 150 years. The overwhelming amount of or attribution of global warming is from carbon dioxide concentrations there at the top, and below it, methane emissions from anthropogenic activities. And most of that has come from energy creation by the burning of fossil fuels, as well as other sources of heating, cooling buildings, things like that. You can see here that actually changes in land use, mainly deforestation, at the same time, has actually caused a reverse. It's actually causing a cooling effect because of the change in how much energy is being reflected from the Earth's surface. But overall, what this is showing is that the overwhelming majority of the warming that we've seen over the last 150 years that we've measured is directly due to human-caused emissions of carbon dioxide and, to a lesser extent, methane. Now, at the same time, we've seen over the last 150 years not only increases in carbon dioxide concentrations, which has increased global average temperatures, but also that's been augmented by deforestation, especially in tropical regions. So we're thinking about deforestation in South America, Central Africa, and Indonesia. So what you can see here is this is a figure put together by a study in 2016 that showed that over the last 30 years, the United States and China have been the largest emitters of carbon dioxide concentrations, but actually more than the entire European Union, the entire country of India, and the entire country of Russia has been carbon dioxide sequestration lost by tropical tree cover loss. So by deforestation, the amount of carbon dioxide that can be taken in or sequestered by trees, that has been cut down because of deforestation in tropical rainforests, and that's actually accounted for a loss of a carbon sink that can equate to even more carbon emissions than the entire continent of Europe or subcontinent of India has put together. So it's not only just carbon dioxide emissions through burning of fuels, but also deforestation that contributes to carbon dioxide concentrations in the atmosphere and global warming. So overall, we have an increase in carbon dioxide concentrations. It can be pretty well connected to human sources. And we see a very predictable response from global average temperature. So what this is showing here, this moving graph here is showing the global temperature expresses an anomaly relative to the 1951 and 1980 mean. That shows over from the late 19th century to the present time period. And the different lines here are showing 4 different data sets, or excuse me, 5 different data sets for measuring that global average temperature. So when we think about global warming, which is often used synonymously with climate change, that's something that's actually not, it's kind of bad practice because global warming is just described as the increase in global average temperature that I'm showing you here with these charts. Global warming causes a change in Earth's regional climates. And because Earth's climate system is so complex, as the schematic that I showed you in one of my first slides illustrates, that this increase in global average temperatures means that different climates react differently. And so that's something to hopefully take home, is that, global warming and climate change, again, they're used, synonymously, but actually global warming, what I'm showing you here, the increase in global average temperatures, is causing climate change. And in reality, you can see that over the last 100 to 150 years, the global average temperature has increased by a little bit less than a degree Celsius, or about 1.5 degrees Fahrenheit. And I can imagine that in many places where we're living right now, the temperature since I began my talk has probably changed by more than 1.5 degrees Fahrenheit. Now, when we talk about the entire global average, that is important. However, it is climate change, not global warming, that really causes the primary impacts to human and natural systems that we're really interested in. Now, when we look at global warming or changes in temperature on a spatial scale here, we see that not every place on Earth has warmed at the same pace. The darker the red on this map, the larger the warming trend has been over the last 100 to 150 years. So you can see that the Arctic, the high latitude Arctic here, has warmed at a much higher rate than have mid-latitudes or the tropics. And I'll describe a little bit of why that is. But because, again, this kind of goes back to, because Earth's climate system is so complex, an increase in global average temperature does not necessarily mean that every place is warming at the same rate. And in fact, there are some places that have, very few, but there are some places that have cooled over the last 100 years. Another important kind of piece of this is climate sensitivity. And climate sensitivity is really answering the question of how sensitive is the climate system to changes in radiative forcing. And so what this usually is defined as is how much will the global average temperature change if we double carbon dioxide and let temperature reach an equilibrium. So actually, this is somewhat timely, because a recent study that was published earlier this year found that re-estimated climate sensitivity and put it between 2.6 and 3.9 Kelvin, which is roughly 4.5 degrees Fahrenheit to 7 degrees Fahrenheit. What that means is that we can estimate that if we double carbon dioxide right now, we go from 411 to 822 parts per million, that temperature will rise, global average temperature will rise about 4.5 degrees to 7 degrees Fahrenheit. And there is some uncertainty there because of climate feedbacks and things like that. Now, again, that doesn't sound like a whole lot. However, I like the Gavin Schmidt, who's a wonderful climate scientist at NASA, puts it this way, that the difference between forests in the Arctic and ice sheets extending down to Chicago is only about 8 Kelvin. And so what that means is that even though that global average temperature change doesn't seem like a lot, because of how much energy that actually represents on the Earth system, it has tremendous impacts on climate change. And that's actually what we've seen here in the Midwest, that, that degree Fahrenheit warming in the Midwest that we've seen over the last 100 years has resulted in some pretty dramatic changes in our climate. And the reason being, the reason that we don't get a consistent homogeneous warming everywhere is because, again, the climate system is complex. We have not only the atmosphere, but we have the oceans transporting energy from the equator to the poles. We have feedback processes, which I'll get in just a little bit. So it's all extremely complex, making different climate change impacts for different regions. So I just want to talk very briefly about climate feedbacks. And part of this is describing why the Arctic region is warming so much faster than other regions. And another reason I want to talk about this is because it is really a fascinating, they are really fascinating processes. And they do have impacts for us here in the Midwest as well. So the climate system is complex. It doesn't act in a simple linear way, whereas I increase carbon dioxide, temperature increases, and we just get warmer. It doesn't necessarily work out that way. Feedback processes are actually the result of global warming. They're caused by the warming itself, but then they act to modify those changes to either amplify them, make for even more warming, or dampen them to make for actually less warming in response. So for example, a positive feedback process increases warming beyond what would normally happen based off of just the radiative forcing from carbon dioxide. A negative feedback actually decreases that warming. So I want to discuss two different feedback processes here that are extremely relevant for climate change. There's the ice albedo feedback and then the water vapor feedback. So the ice albedo feedback is really relevant in high latitude regions, the Arctic and to a lesser extent Antarctica. Albedo, just to set the stage here, albedo describes a proportion of radiation that's reflected by a surface. So the brighter the surface, the more reflection there is, the higher the albedo. So for example, newly formed snow has an albedo of about 0.9, meaning 90% of the radiation that comes in that hits that snow surface will be reflected, which means that only 10% will be absorbed. And remember, if a surface absorbs more energy, the temperature is going to increase. So sea ice has an albedo anywhere between 75 and 90%. Meaning, again, 75 to 90% of the energy that hits that sea ice is going to be reflected and presumably reflected back into space. So as we have global warming because of carbon dioxide concentrations, the Arctic warms. And the air in the atmosphere in the Arctic warms, and therefore it melts that sea ice. Now, when that sea ice melts, as you can see here from the picture on the top right, it exposes open ocean water that is much, much darker. So just as a reminder, the geographers in the room, that even though Antarctica is a landmass, the Arctic is a large ocean. So the sea ice is forming on top of ocean water, and when that sea ice melts, it exposes that much, much darker ocean water. The schematic on the bottom here shows that as we melt that sea ice, the albedo of that surface goes from 90% to 6%, which means that instead of absorbing only 10% of the sun's energy that hits that surface, we're absorbing 94%. The way that I like to talk about it with my students is that if you take every concrete surface in wherever you're living and pave over it with asphalt, right? And then you think about a nice hot summer day, it's going to change the way you're going to walk around barefoot because that asphalt surface is going to absorb a tremendous amount more energy. And so what we have, because of the initial warming from carbon dioxide concentrations, we have a strong trend, a downward trend in Arctic sea ice concentrations. Again, timely, you can see here on the right, this is a map that shows the concentration in 1980 of sea ice, all the extent of sea ice all the way around the Arctic. And I apologize, as a geographer, I can just switch to map projections, but what we're looking at here is a polar projection in this map. So Greenland's right here, northern Canada, Alaska's right here. So this is the Arctic here, and you can see the 1980 concentration goes pretty much all the way around the Arctic Ocean. 2012 was the previous low, and that's what we can see. This entire area here in 2012 was open ocean, meaning that that large area, roughly the size of the contiguous United States, instead of it being high albedo sea ice reflecting a ton of energy, it was low albedo ocean water. And so what that means is that large scale change in albedo can actually mean that the entire region takes in more energy and then holds on to that energy during the wintertime and it expels it back to the atmosphere warming that area, which means that the ice albedo feedback is a positive feedback because we're getting the warming and the exposing of that open ocean water, changing the albedo. We warm the atmosphere in the Arctic. Now, interestingly enough, this year you can see here that our latest sea ice measurements are actually showing that this year in 2012, in 2020 this year, we actually had our lowest Arctic sea ice extent on observed record. And so what that means is that we will likely see an acceleration of that warming for the next couple of years. I don't want to get into Arctic climate too much, but there are different types of sea ice in the Arctic. There's the types of sea ice that forms and melts every year, the annual sea ice, if you will. And then there's the perennial or long-term sea ice that forms in a given year and then maintains ice during the summer so that it just grows over the next year. We're actually losing a lot more perennial sea ice than we are annual sea ice. And what that means is once that perennial sea ice melts, it's much, much more difficult to form that than it is the annual sea ice. And the annual sea ice tends to be a lot thinner, therefore the albedo is lower in general. So overall, that ice albedo feedback, what that results in is what we call Arctic amplification. So the global average temperature is increasing, but because that sea ice is melting predominantly in the Arctic and changing that albedo, changing the energy balance of the entire area, we have a much larger warming rate in the Arctic than anywhere else. Because the Arctic sits on top of the world, it has a major impact on mid-latitude climates like ours. And so as far as the the impacts of Arctic amplification staying in the Arctic, it doesn't necessarily work that way. We do see changes in our climate because of this. The second feedback process I want to talk about is water vapor feedback. This one's a little bit more simplistic. So overall, warmer air has a higher saturation mixing ratio, means that warmer air can, quote unquote, hold more water vapor. It can hold more humidity because of its higher temperature. What that means is that as we increase air temperature globally, we also increase evaporation, because the air can take in more water from the surface or from the oceans. So more evaporation means more humidity. And if you remember back, water vapor or humidity is a greenhouse gas. It's actually many more times more powerful than carbon dioxide and methane. So what that means is the initial warming of global warming increases water vapor content in the atmosphere. And that's what I'm showing here at the bottom, this plot. This is global specific humidity, just the total amount of water vapor in the atmosphere, both from land and ocean. You can see that increasing trend going back to the 1970s. So with more water vapor, with more humidity, it actually feeds back, enhances the greenhouse process, the greenhouse effect, and increases our warming. So this is another positive feedback because of that. Interestingly, though, when I talk about impacts to Illinois, it's the water vapor feedback that is actually making it so that summer is the only season in Illinois that has not significantly warmed. And I'll talk about that in a little bit. But overall, when we think about a global perspective, the water vapor feedback enhances or is a positive feedback. So it enhances that warming. Okay, so let's get drilled down a little bit more to Illinois. So some observed changes. I'm going to be light on impacts because that's for the second talk next week. But I do want to talk a little bit about what we felt here in the Midwest. So over the last 120 years, which is really where our observations go back to 1895, statewide annual average temperature has increased by about 1 degree Fahrenheit over the last 120 years. So if we just take the annual average temperature, plot a line to it, it's increased by about 1 degree Fahrenheit. When we break that down seasonally, the warming trends in winter and spring are much larger than they are in summer and fall. I have these county level maps here that show that change. So you can see here that winter and spring, the darker reds indicate a much larger degree of warming than in summer and fall. And actually, if any of you are in the very southeast tip, Massac, Gallatin, Hardin counties, there actually hasn't been warming. There's been a slight cooling of summer and fall temperatures. My table here that I'm showing is showing those trends in temperature as expresses degrees Fahrenheit per decade. And we break it down from mean temperature, maximum temperature, and minimum temperature. So again, winter and spring, our warming rates are pretty high. Fall is warming, but to a lesser extent than winter and spring. And I'm sorry, I'm so used to climatologist speak here. I need to take a step back. Winter is defined as December, January, and February. Spring is defined as March, April, and May. Summer is defined as June, July, August, and then fall is September, October, and November. One thing that's interesting here is that you see the summer warming rates, particularly for mean and maximum temperature, are very low, much lower than other seasons. And actually, the summertime maximum temperature over the last 120 years has decreased. The reason being is that we have gotten much more humid. Our summer humidity has increased to a large extent in Illinois. What more humidity does is it makes for more cloud cover. If you think about what more cloud cover can do in the summer, it means that there's less radiation coming into the surface during the day, so our daytime maximum temperature is lower. But on the flip side, clouds tend to trap more energy at night, and therefore it increases our nighttime minimum temperature. So you can see here there's this kind of contrast between a cooling trend in summer maximum temperature and a large warming trend in summer minimum temperature. And so that is a really important thing, that we see the largest change consistently in daily minimum temperatures because we have that increase in humidity. Oh, too fast there. Let's talk about precipitation. So arguably, actually becoming inarguably, really, precipitation has changed more, and the impacts from changes in precipitation in Illinois have been really the largest that we've seen over the last 100 years or so. So annual total precipitation statewide has increased by about 5 inches between 1895 and 2019. However, when I break it down by season and by region, northern, central, and southern Illinois, summer precipitation has increased much more than other seasons. So the summer trend in precipitation is 2 to 4 times larger than that in other seasons. And that contrast is actually largest in southern and northern Illinois. So you see southern Illinois here, the summer precipitation just for summer has increased by about 3 inches over the last 100 years in southern Illinois. So overall in Illinois, we are getting wetter, and we are getting wetter in every single season and in every single region as well. Now, as far as impacts are concerned, and again, I'll speak a little bit more to this next week, we haven't just seen total precipitation increase, but precipitation intensity. And one way to represent this is to think about the total amount of precipitation that falls as a recurrence interval. So some of you may have come across this with floods. Think about the 100-year flood, right? The 100-year flood is just a flood stage that has a 1% chance of happening any given year. And that way we could say, here's the 100-year rainfall event. Now, here at the Illinois State Water Survey, we actually just finished a study re-estimating recurrence intervals for precipitation. So to say, what's the new 100-year precipitation total? The old recurrence estimates that I have here in this column are from 1989, and these are the new ones, so 30 years later. And what I like to do when I talk to folks about precipitation intensity is I like to use current events. And 2020 has given me plenty of events to talk about. So I'll take this one here from July 2020 in Peoria. So the Peoria Airport recorded almost 6 inches of rain in 6 hours. Now, based off of the old recurrence interval, that was a 250-year event, meaning that it has about a 0.25% chance of happening any given year. So pretty rare event. Based off of changes in precipitation just over the last 30 years, that event has gone to a 100-year event, which means that this precipitation event, the flash flooding that came along with it, if any of you are in central Illinois and the Peoria area, the flash flooding that came along with that has actually now a 1% chance of happening any given year, which means the probability of that kind of intense event happening, that type of intense rain, has increased 2.5 times over the last 30 years. Another good example is here in southern Illinois at Scott Air Force Base in Belleville. They got over 5 inches of rain in 3 hours. And the probability of that has increased by quite a bit as well. So overall, we're seeing a change not only in total precipitation, but precipitation intensity that causes increasing in flooding. And again, next week, I'll talk a lot more about impacts and what that's having impacts in the state of Illinois and Midwest more broadly. Okay, so let me get into a little bit about climate projections and talk about the future. So climate projections are predictions of what will happen under a set of assumptions. So in order to figure out or to project how climates will change into the future, we run climate models under a bunch of simulations under an assumption of how we expect greenhouse gases and radiative forcing to change in the future. And those are often called representative concentration pathways, or RCPs. There's 3 or 4 RCPs that are often used. There's 4.5, 6, and 8.5. Those relate to the amount of forcing that we expect to have by the end of the century, by 2100. 8.5 being the very top forcing. You may have heard that as the high emissions scenario. That is, if we continue to have carbon dioxide emissions that have been going the last 20 years, continue at that rate until the end of the century. And the contrast of that is 4.5, where we actually curb carbon dioxide emissions over the next 10 to 20 years and go out from there. And so based off of these scenarios, we can run our climate models and say, okay, if we have this much warming, this much concentration of carbon dioxide over the next 60 to 70 years, here's what our climate change is going to look like. But if we have less warming, here's what our climate change is going to look like. I'm going to skip these next 2 slides. We can talk about these a little bit more if folks have questions. It just talks about uncertainty in the projections, but I really want to get to what we're actually seeing. So as far as projections of temperature in Illinois are concerned, what this is showing, what these figures are showing here for northern, central, and southern Illinois are the spread in model projections of mean temperature going all the way out to the end of the century, right around 2100. The black line here, the solid black line there, is the historical mean over the last 30 years or so. And so what you can see overall is that these plots here, these area plots, are increasing. So overall, projections indicate continued increases in temperature in Illinois across all seasons. The very right-hand plots here don't show mean temperature. They actually show the projection of the annual number of days where maximum temperature gets above 95 degrees Fahrenheit. So for both average temperature and for the very extremes, our heat waves, what this is showing is that projections are indicating a high certainty of increases in both mean temperature and extreme temperature or heat waves. However, the difference between the red and the green areas indicates the difference between the high emission scenario, lots and lots of continued carbon dioxide emissions, and the low emission scenario, if we curb those emissions. And what we can see is there's a clear separation between the red area and the green area in every single region of Illinois. What that means is that the magnitude of temperature change is very dependent on the emission scenario. Therefore, fewer emissions now and into the future, fewer carbon dioxide emissions, means less warming. So that means that if we want to reduce the total overall warming and the frequency of extreme temperatures and heat waves, that we have to reduce emissions. And by doing so, temperature, because it's so dependent on carbon dioxide, will follow suit. So that is something that is of interest. Now, when we talk about precipitation, it's a little bit different. Projections from climate models actually show continued increased precipitation and precipitation intensity, and some seasonality to that. Spring is expected to get wetter, summer is expected to get a little bit drier. However, when we look at the actual plots of the spread of models, the projections don't actually separate like they do for temperature. So what that means is that, you know, reduction in carbon dioxide emissions does have a direct impact on further or future warming in the Midwest, but precipitation isn't very dependent on that. So it's likely we're going to see continued increases in precipitation, as well as seasonal variability in precipitation, regardless of carbon dioxide emissions between now and the next couple of decades. Okay, last two slides. I just want to hit on a couple of results of climate change or impacts from climate change. And I'll get into the specific impacts more next week, but a big one here is global sea level rise. So warming, the global warming over the last 100 years has caused global sea levels to rise considerably. It's caused by meltwater from ice sheets. So ice sheets, sea ice, glaciers, they melt. That meltwater runs into the oceans. The ocean, the sea level rises. It's also caused by thermal expansion of the water. Water as a liquid expands as it's heated, and therefore global warming causes the water in the oceans to expand, and therefore the actual level of those seas rise. Now, global average sea level has risen by about 200 millimeters since 1900. However, about 90% of that has been in the last 30 years, which means that actually the rate of sea level rise has accelerated. There is very high confidence, about a 90% chance of global sea level rise of an additional 200 millimeters by 2100. And likely it will be more than that because of continued melting of ice sheets and sea ice. Now, again, I'll talk about specifically the impacts of global sea level rise as they are all encompassing. But that's when people talk about sea level rise, that's really the science behind that. The last thing, and this is directly related to sea level rise as well as increases in extreme climate events. But we have a climate migration as an impact. And you may or may not have heard the term climate refugee. That is actually not the best way to refer to this process. Climate migration is a much better term. So to give you an idea, in 2018, there were over 1 million people, 1 million Americans that were displaced due to natural disasters in the United States alone. 1 million people. And it is expected that between now and 2050, there will be over 100 million people globally who will be permanently displaced because of global sea level rise, because of natural disasters that are due to climate change, and because of conflict, global conflict that is also due to things like water restrictions and things like that because of climate change. And so I put this up here because when we think about climate change, especially around impacts, we think about things like more frequent hurricanes or more frequent flooding or larger, longer droughts or more extreme heat. We don't necessarily think about the societal or political impacts of something like displacement of many, many, many people and large scale migration, both within the United States and internationally, because of that. So that is a tremendous impact that is already going on because of climate change and is expected to continue into the future. And like I mentioned, I'll have a little bit more details about that, about migration and climate migration next week as well. So overall, I have the summary up here. Instead of rehashing these same points, I'd actually like to get in discussion and questions because I probably went over my time like always. So again, I just want to, I have my contact information here. And I want to thank again Megan for letting me present here, and I'd be really happy to take questions and discussion about any of this. And I have all of my contact information here. So anyone with questions about anything, data needs, resources for information about climate change, please feel free to reach out to me anytime. With that, I again want to thank you for letting me present.
Thanks so much, Trent. That's a lot of information, right?